Welcome to Introduction to Metals. Today I'm going to review the main categories of engineering materials. Then I would move on to concentrate on introduction to metals. We would talk about metals and some applications. And in subsequent lecture, we would actually take a closer look at ferrous and non-ferrous metals. The four main categories of engineering materials are metals, plastics or polymers, ceramics, and composites. Let's start with metals. Those that are based on ferro. The iron itself is called ferrous material, and those that are based on other material are called non-ferrous metals. An example of ferrous is steel, stainless steel, die and tool steel, and cast iron. And examples of non-ferrous metals, I'm sure many of you guys are familiar with some of these metals, are aluminum, copper, zinc, titanium, and so on. Polymers also include a major category of engineering materials. They are divided into three major categories: thermoplastics, thermosets, and elastomers, and some examples from each category is given here. For thermoplastics, the one that's almost everybody is familiar with is PVC and nylon. Thermosets, there are epoxies and polymers. They set over time and with temperature, whereas thermoplastics are more different. They're also very sensitive to change in the temperature, but not as much as other types like elastomers, rubber, silicon, and so on. So we would talk about all of these materials in due time, but for now I'm going to give you an overview, and then today I'm going to concentrate on metals. Other two main category of engineering materials are ceramics. They are the most common ones, or the most famous ones, are diamonds, and of course glasses, and glass ceramics, and so on. Composites also play an important role in materials, in the type of materials. They're a major category of an engineering material, including reinforced plastics and laminates and so on. And their applications are well known in the aerospace industry, and recently, starting about 30-40 years ago, we start applying composites to some of our civil infrastructure for rehabilitation purposes. As we have mentioned previously and discussed in previous lectures, properties of materials, they are classified into two major categories: mechanical properties and physical properties. Mechanical properties describe the behavior of the material under the application of the loads, and physical properties, they give us some properties of the material that are significant to any design. Mechanical properties include yield strength, ductility, hardness, ultimate strength, and so on. Physical and chemical properties include thermal conductivity, thermal expansion, corrosion, density, and so on. Both mechanical and physical properties of the material they're very important in material selection and material engineering. We also have talked about material strength in general. We talk about the stress strain diagrams, and I'm going to mention here again that stress strain diagram is perhaps the most widely used diagram in material and dealing with material strength. Much information can be extracted from a stress strain diagram, including the yield strength, including the slope of the diagram in the elastic range, which would give us the modulus of elasticity. In the inelastic range, of course, the slope is constantly changing, and we can calculate the modulus of elasticity using the slope of that a particular point on that curve. We can also extract the ultimate strength of the material, also fracture strength of the material from a stress strain diagram. Remember the way stress and strain was defined here, and as such you would be more familiar. Well, you'll be familiarize yourself more with what we mean with some of these terms that I'm going to go over here. A different grade of steel is shown here in this figure. The stress strain diagram is drawn here for 4 different types of steel. One is the tempered alloy steel, A709. That's this diagram here. Then the high strength low alloy steel, A992, is given here. Then the carbon steel, a very common type of steel, A36 is shown here, and pure iron is shown here. So as we are playing around with the carbon content of pure iron, after we adding carbon to pure iron, you can see that we can achieve different properties for the same with the same base material, which is pure iron. So we're going to add carbon to pure iron, and we would get different grades of steel according to the carbon content as it is shown here. The quenched tempered alloy steel, A709, has much higher strength, but its strain is lower compared to other types that are shown here. High strength low alloy steel, A992, it has a lower strength in comparison with tempered alloy steel, but it has a higher strain. Carbon steel has a lower strength than the other two that I just mentioned, but it has a much higher strain. The strain here plays a very important role in defining the ductility of the material, in this case a different grade of steel. Of course, the more ductile the steel is, depending on the application, it may be more desirable. There are other types of materials, plastics, shown here, more sensitive to the temperature change. From 40 degrees Fahrenheit, the strain is much less. As we are increasing the temperature, we reduce the strength and increasing the strain, and so on. So this last one down here, the strain is almost 1/3 of the one that's shown up here, but the strain is also 3 times or more. Again, that would help us with determining which material is more ductile, depending on the application that we want. We may have a design that requires a much ductile material and less strength, and so on. So again, picking the right material is really an art, and sometimes with some trial and error, one should be able to pick the right material for the design. Natural rubber also is an interesting material. The strength is not much, but its strain is very high. This curve, the last curve on the bottom right hand side of the screen shows the stress strain diagram for concrete. And this area up here between this area of the stress strain diagram shows the properties of concrete in tension, and this lower area on the lower left hand side shows the behavior of concrete, the properties of concrete under compression. As you can see, the compressive strength, and this is really not to scale, but it's provided here for illustration purposes to illustrate the point. The compressive strength of the concrete is much higher than the tensile strength of the concrete, and that's expected in order to compensate for lack of strength in tension. Reinforcement are used, making reinforced concrete a composite material. So we're going to take a closer look at alloys and phase diagrams. We're going to take a look at ferrous metals, non-ferrous metals, super alloys, and guide to the processing of metals. We're not going to take a look at all these topics today. First, we're going to take a look at alloy and phase diagrams. So let's get started. Metals are the most important engineering materials, and there are many reasons for that. The most important one is or are the properties of metals that would satisfy them for a wide range of applications. Second thing is the manufacturing processes of metals have been developed over the years and have been refined, and in general, engineers and people that are working with metals, they have a much better understanding of the material. The behavior of the metal is not as surprising as it was at the beginning of the development of other materials. However, because of their weight, the application became as we advanced the technology and the industry. Composites are used in most of the aerospace vehicles, and also the defense industry and other types of material. They're also widely used nowadays in cars, whereas in the past, 30 years ago, the application of composite in cars weren't as wide as we see it today, simply because of economical reasons and what people preferred at that time as something that's more popular. Remember that many times we need to look at the other side of the equation, which is after we build or we make the design, and now we need to be able to make sure that it works, and that's why where prototyping and other types of subjects would come into play. So why metals are so important? What is it about metals that make them so important and make them so popular? Well, because they have high stiffness and strength, and they can be alloyed for high rigidity, strength, and hardness. It's not that difficult to make a metallic alloy. They're tough, and as such, they absorb the energy much better, and they have higher capacity to absorb energy. Metals are good electrical conductivities, and in some applications we would like the material to have good electrical conductivities. They're also good thermal conductivities. They conduct heat better than ceramics or polymers, and they are cheap in comparison with other types of engineering materials. And as I mentioned previously, we have a much better understanding among the engineering community of the metals. We understand metals very well. So, what are the starting forms of metals used in manufacturing processes? Well, cast metal is the starting point. It's a starting form. Wrought metal and powder metal. So we can either have a cast metal, a wrought metal, or powdered metal before we can start the process. The main classification, two major categories of metals, as I mentioned, are ferrous and non-ferrous. And there are also super alloys that we are going to talk about in short in due time. Some metals are important as pure elements. Examples are gold, silver, copper. Most of the precious metals fall in that category. Of course, they cannot be 100% pure because of many reasons. For example, 100% gold is too soft and it's very difficult to make any kind of use it for any kind of decorative purposes or jewelry. Most engineering applications require the enhanced properties obtained by really mixing different types of materials and make an alloy. Well, we are going to get into that shortly. Through alloying, we can achieve some of the properties that are desirable, including increased strength, hardness, and other properties compared to pure metals. Excuse me. So, what is an alloy? An alloy is a mixture or a compound of two or more elements. Out of that two or more elements, one of them must be a metal. There are two main categories. One is the solid solutions, and the other one is the intermediate phases. The solid solutions is an alloy in which one element is dissolved in another to form a single phase structure. What is a phase? A phase is any homogeneous mass of material, such as a metal in which the grains all have the same crystal lattice structure. So there are some key words here one must learn. One is, when we talk about phase, we're talking about a homogeneous mass of material. And it is also important to realize that the structure of the grains, when we talk about the phase, must be the same. In a solid solution, the solvent or base element is metallic, and the dissolved element can be either metallic or non-metallic. In other words, we have the metal and we add something to the metal. So that's really the basic of that. There are two forms of solid solutions. One is the substitutional solid solution. Substitutional solid solution. I'm going to go back here. Yeah, I'm going to take a look at item 1 or 2 shortly. Substitutional solid solution, and this is the other word that I'm sure most of you guys may not even know how to pronounce. I'm sure many of you do, but let's practice with this. So in a substitutional solid solution, atoms of the solvent element are they are replacing in its unit cell by the dissolved element. An example is shown in part A. A best example is brass. Brass is when we dissolve zinc in copper. In that case, the atoms of zinc would replace unit cells of copper as shown here. However, in interstitial, right? Remember that word, interstitial. Interstitial, okay? Interstitial. The way I put it here, I'll also give you the pronunciation, interstitial, okay? The interstitial solid solution is another type of a solid solution. In that case, the atoms of the dissolving element would find the vacant spaces between the base metal atoms, and they're going to sit there as shown here. An example is, for example, these black dots here. They represent carbons that is dissolved in iron to form steel. There will be no replacement here. It's just the other material is going to find the spaces between the atoms, and this atom is going to fill those spaces. As we are solving an element into another, there's a point in which we reach the limit of the solubility, and beyond that point, it is not possible to dissolve the element in the alloy anymore because it exceeds the solid solubility limit of the base metal. As such, a second phase forms in the alloy, and we call that an intermediate phase. The intermediate phase is used to describe the chemical composition in the intermediate between the two pure metals. So it's neither nor. In this case, the structure, the crystalline structure, is different from those of the pure metals. Let's take a look at some types of the intermediate phases. There are two types. Number one, the metallic compound, FeC, well, Fe3C is an example. It consists of a metal and a non-metal, and then the intermetallic compounds. So we have metallic compound as an intermediate phase, and we have intermetallic compounds. In this case, we have all metals, two elements, and they're both metals, and of course they have their own properties in some alloy compositions. The intermediate phase is mixed with the primary solid solution to form a two-phase structure. And why is it so important to look at the two-phase alloys? Because they behave very interestingly. They can be heat treated for much higher strength than solid solutions. So that's why they're of importance when we study engineering materials. You've probably heard the term before from your other courses, but let's talk a little bit about phase diagrams. Phase diagrams are nothing but the graphical representation of different phases of an alloy system as a function of composition and temperature. We're going to take shortly. We're going to take a look at a binary phase diagram for an alloy system. It shows both elements at atmospheric pressure. On the horizontal axis, we draw the composition, and we draw the temperature on the vertical axis. Any point in the graph shows the composition and the phase or phases that are present at different temperature under equilibrium conditions. Here's an example that I'm going to go over here. This is a copper nickel alloy binary phase diagram. As I mentioned, the composition is shown on the x-axis and the temperature is shown on the y-axis in both degree Fahrenheit to the far right and in degrees Celsius to the far left. Let's take a look at the x-axis here. At the point of 100, there is an element right next to it. This is the point of 100% nickel, and to the left where it shows 0, this is the point of 0 nickel. That means it's 100% copper. This is a very smart way of showing the composition of the material. However, one should not be confused, because down here it shows the percent nickel. So when we're talking about percent nickel in this case, we may have another diagram that shows a percent copper, but since this diagram shows a percent nickel, in that case, at this point there's a 0 nickel, which means 100% copper, and at this point is 100% nickel. So we need to extract certain information when we look at this graph. We need to be able to see what this graph really means. Why do we need to use the binary phase diagram? Why are they so important in the discussion of materials? As you can see, this diagram shows a solid solution, a liquid solution, and there's a phase in between liquid plus solid that's marked here by this area in here. So if you look at the this portion of the curve that I'm going over, from this point down, the alloy is solid. Okay. From this line that I'm showing up here to the left of this line, you continue this line, to the left of this line, that is the liquid solution. That means as we are increasing the temperature, we are going to make an alloy like a liquid solution. Under this temperature, as I show under this line, the alloy is solid. And there's some phase in between, and that is between these two lines, between this line and between this line, as shown on this graph. Well, they're not really straight lines, but between these two curves that shows the liquid and solid states. And of course, there would be some instances in which in that liquid plus solid, there would be more liquid than solids, and there would be, or there could be more solids than liquid. So it's not like we increasing the temperature and it's going to melt instantaneously. As we are increasing the temperature, we see that at some point there will be liquid plus solid phase that's formed. As you can see, let me take a look at this particular line here, the LCS line LCS is a straight line. Let's start at, for example, we have a copper nickel alloy binary phase diagrams, and we want to work with this alloy, but we have no idea. We go to the laboratory and somebody hands us a copper nickel alloy and say, I want you to completely melt this alloy and tell me what the temperature would be. Okay, so you would grab that alloy and take it to the laboratory. Let's say in this case you know the composition. There are occasions in which we don't know the composition, and we are going to pretty much look at different phase diagrams to be able to determine what would be. That's one of the ways in which we can determine the composition of an alloy. There are also other methods that are pretty advanced in the industry, but we're going to concentrate on the basics. For example, so you would take that alloy to the laboratory, and knowing that it is a copper nickel would give you a lot of information, and you can pretty much start heating that up. The alloy if you want to come up with percentage of copper and nickel, you can start at some point by really heating this up. Let's say that you start pretty much melting this alloy, and after it becomes completely liquid, you measure the temperature, and it shows that it melts at 1260 degrees Celsius right here. So at this point, there's no solid in the alloy. It is completely liquid. And you mark that temperature and you measure that. Let's say it happened to be 1260. Okay? And then based on that, you want to know what would be the percent nickel in this particular alloy. So knowing that it's going to, you already know that it is nickel alloy. So that's how you refer to this phase diagram. If you don't know what that is, then you need to look at other phase diagrams. But for the sake of argument, let's say you know the composition is copper nickel. So after you measure the point in which it becomes completely liquid, then you would have this graph in your hand, well, in front of you. You would look at this graph, and you can actually draw a straight line from that melting point. Let's say if in this case, if we assume it was 1260 degrees Celsius or 2300 degrees Fahrenheit, then you would continue that line, and it is going to hit the diagram at some point. Okay, and based on that point, then you can extract much information based on where it actually hit the diagram. Let's assume that in this case it hit the diagram right there. Okay, and you knew that there were another temperature in which it actually started melting. So you know the temperature that it got completely melted. Then you know the temperature that it started to melt, which is usually the same temperature, the same temperature, but depending on the percentage of nickel, it would be a variable. So in this case, you would continue this line all the way until it hits the point S, and you draw a straight line down, and that would show it's going to hit the x-axis at 62%, and you know exactly that 62% is the composition of nickel, 62% nickel for that particular material. So this is really the way we can pretty much come up with the different composition of the material, the basic way, I should say. So if the temperature could also be different if you have melting temperature at different points, or complete, passing the liquidus curve, it could be different. At this particular point, for example, the percentage would be different. If it's 50%, of course, the phase here would be different. So note that if you draw a horizontal line, not all of them would have the same length as LCS. So again, we can extract much information from these diagrams, including the composition of the material. So they're very useful diagrams. If we want to do the 50%, if you want to do the same thing with a 50% nickel in a copper nickel alloy, and then we can again continue that line. At some point, it's going to hit the solidus, and we would draw a horizontal line at that intersection of the vertical line drawn at 50 and the solidus curve at the intersection. We're going to draw a horizontal line, and anywhere it is going to hit that temperature, and we know where would be the melting temperature for that particular alloy would be, and so on. So again, depending on the composition of nickel, you're going to have different numbers here, different temperature. As we are reducing the nickel content, you see that the temperature or the melting point would actually decrease. So if you have 100% copper, the melting point is shown here. If we have 100% nickel, the melting point is going to show here, depending on the percentage and how much we want the melting point to be. We can add and subtract the amount of nickel to this composition. As we are increasing the amount of nickel, we are increasing the melting point of the alloy itself. So this would be a very useful diagram in determining that. So for a copper nickel alloy system that I just described, solid solution alloy throughout the entire range of composition below the some of the properties of this alloy system is there is no intermediate solid phase in this alloy system, and there is a mixture of phase in the region bounded by solidus and liquidus curves that I just showed. And we've already discussed this, that I just put it in text here. Eutectic alloys, they are a particular composition in an alloy system for which the solidus and liquidus are at the same temperature. The word eutectic derived from the word Greek. There's a Greek word eutectus, meaning easily melted. Those that are Greek, or those of you that are familiar with Greek language, you know what I'm talking about. It means easily melted. Eutectus, of course, is an older term that's used. Eutectic alloy, again, is a particular composition of an alloy in which we can have solid and liquid at the same temperature. It's a special composition. And the eutectic temperature is a melting point of the eutectic composition, and the eutectic temperature is always the lowest melting point for an alloy system. That brings me to the end of the slides that I just discussed today. If you have any questions or comments, feel free to send them my way through the course website. I hope you find these material useful in your learning. Thank you.